Okay, class, so here's the example I said we would go through today online. So the question is looking for the cross-sectional area A. So I want you to determine A. If the maximal allowable is equal to 150 megapascals. The beam is shown below. Okay, so I've written out the steps here for the first part of this solution, which was determined Y and A. Try to stay organized and follow through with the A for the first part and the second part. Then I calculated I, so I've written that all out for you as well, so you can pause the video and look at that. Second set of this is the equations of equilibrium. And so for global equilibrium, I have RA, RB, minus 60 minus 80 is equal to 0. Then I take the moment at A, RB, the 60 and the 80, and I can solve for A and B. Third step, find the functions. Now remember, this is why I've shaded it. So you have to have functions that describe this area and functions that describe this area, and they are different loading. So again, I'm going to use the method of integration. So the load equation for the first part section from 0 to 2 meters is minus 40. I'm going to integrate, and so I get minus 40x plus C1. Boundary conditions at x equals 0. We just have the value of RA, which is 10. So therefore, C1 is equal to 10. Therefore, our equation is minus 40x1 plus 10. Same with the shear. Now I'm going to integrate this again. So I get minus 20x squared plus 10x1 plus C2. Boundary conditions from at x equals 0. Well, there is no moment, so therefore C2 is 0. So the equation for M1 is minus 20x squared plus 10x. Section for x, the distributed load function is just 0, right? It's a concentrated load. Take the integral, you just end up with C3. Now, this boundary condition is a little bit different. Basically, what you do is you want to look at x equals like 2.000001. Okay, so we have to be in the other section of the beam. But we know actually what all the forces are. So this is 2. So at V, the shear at 2 is equal to C3. We've already determined that because here is our shear function. We have C3. Okay, it's just equal to C3. So, so we have our 10, we have our 130, we have minus 80 due to this distributed load, and then that is all equal to 60, which is at the end of this beam. So this part, we're just using the boundary conditions to say what is the shear in the beam, but we're really in this side of things, okay? So all the shears, you're kind of just putting them all together. So, or you could say minus 6 equals 0, okay? Okay, so the function for the shear is just 60. We integrate again, 60x2 plus t4, and now we're going to do the moment. The moment at as x equals the 2.00001. What is the bending moment? Now you can actually do it from this side or this side, but I'm just doing the 1. And yeah, you could do it from this side too. So you could say it's 60 times, it's only 1 meter away. Okay. And then 1 meter here, or this one's 2 meters. Okay, so the bending moment is the 60 kilonewtons. That's the shear at 60. Right, we just determined what that was. So the shear at x equals 2 is 60 times the distance of 2 meters away is 180. Therefore, the function is 60x squared minus 180. Step 3 is to plot the functions. Now, remember your order of lines, which I've drawn over here. The point load and the linear sorry, I'm going to break this down here. So order of lines. So you know the shape of these functions, and you can determine the endpoints by subbing any of the x equals values into either the shear or the bending moment of the 4 equations. Okay? So you end up with, and again, where the shear is 0, the bending moment is maximum, so that will help you with aligning that. Okay, then the last step of this was the allowable. We're going to need that, but we also need to determine what the maximum bending moment is. So that was our m y over I. And now this is a unique situation too, because we actually have 2 shear values. And so we have to test those in both spots. We have to test it at the top or the bottom. And that's what I've done here. So the whole height is actually 2a over 3 plus the a over 3, that little part, which is just a. So the total height is a minus 5 over 12a is 7 over 12. And so you have to test at the top and the bottom. Remember where it's like pulling away, this is in tension and this is in compression. One thing I did want to notice, if your bending moment values were similar, like say you had 22 and I don't know, 24 and they were positive, I would actually test both of those, right? Because you're going to be timesing y, or the total minus y. Okay, so you'd actually have 2 times and 2 times the tension. Because my values are so small, I'm just going to take that 60 and I'm going to multiply it by the top and the bottom. But if your values were similar, you'd have to test all of them. Okay, so it's really, a minimum of 2, maximum of 4 things. So I just wanted to share that with you because we haven't done that in class. Okay, thanks.